Hello everyone, I'm Kenji Tojo, a second-year master's student at the University of Tokyo. Today I'm going to talk about a motion compression algorithm using a neural implicit representation and the frequency adaptive Fourier feature. Character animation is essential in many video games. Under the hood, these animations are typically implemented using state machine that stitches together a bunch of animations given the user's controller input. In real life, the state machine is very complex and contains tons of animation sequences. Hence, compressing animation sequences is important to utilize the limited storage resources and implement immersive animation systems. There are many works for compressing motion sequences. However, previous techniques requires handcrafted algorithm to exploit smoothness and redundancy in the natural motion. In contrast, neural networks can learn important features of the data. Recently, neural implicit representations have been applied to various types of data, including 2D images and 3D shapes, and shown to be able to reconstruct highly complex data with a compact neural network. That means they can work as learning-based high-quality compression algorithm for general data. In this research, we investigate neural motion compression, a learning-based algorithm to compress character motion sequences. Given an animation sequence, our goal is to automatically find its compact representation without losing the visual quality. So let me first talk about our pose parameterization. We represent an animation as a matrix consisting of n animation frames, each of which represented by an m-dimensional vector that stacks the translations and rotations of the character bones. Because character motions are often continuous, we can also think of the motion as a continuous function of time to pose. That means a time t in the normalized interval is mapped to the character pose y at the corresponding animation frame. We encode this function as a neural network. This means we train the neural net so that it predicts the character pose given any time in the normalized interval. This neural implicit motion representation can compress the data because the number of the neural net parameters is usually much smaller than that of the original dense recording of the pose at each frame, which is the size of the matrix Y. So we know the input and output of the neural net and have the animation sequence as training data. Now we can train a neural net like MLP or multi-layered perceptron. However, there's a challenge in this representation. The input to the neural net is just a one-dimensional and linear time signal. In contrast, the character pose is a high-dimensional and complex signal. Fitting an MLP to such a complex relationship often results in a high reconstruction error. In fact, This is a common challenge in neural implicit representations. In the case of the image, input 2D coordinates x and y are mapped to the RGB image that has rich, high-frequency details like this lion. And directly mapping the 2D coordinates to the RGB value using an MLP gives us a high reconstruction error. Previous implicit networks relied on a technique called the Fourier feature to overcome this problem. Tansik et al. First maps the coordinates to the Fourier feature and then apply the MLP to obtain high-quality reconstruction. The Fourier feature is basically a high-dimensional encoding of the input coordinates using a trigonometric functions with various frequencies. We draw inspiration from these studies and use the Fourier feature to reconstruct the motion sequence from the time signal. In our case, the 2D coordinates correspond to scalar time t, and the RGB image to character animation y. In this study, we also add the original t to the Fourier feature, because such linear component is often seen as a root translation of, for example, walking or running characters. Next, let's take a closer look at our network architecture. Given time t, we first map it to the Fourier feature, which has 2k plus 1 dimensions. We then apply 2 neural net layers, both of which is twice as wide as the Fourier feature. And finally, output the character pose y. As the number k of the Fourier feature frequencies determines the size of the network and thus the compression performance. Carefully choosing a few but useful frequencies is important in our neural motion compression. Previous works of Fourier feature typically uses stochastic sampling from, for example, Gaussian distributions. However, this can add many unimportant frequencies to the Fourier feature. Because human motion often has cyclic components, such as walking legs and swinging arms, there should be a small, important set of frequencies for each input animation. So, we adaptively determine a few but useful frequencies while network training. Next, I'll explain our training algorithm. Once the first training with our trigonometric features is completed, we compute the difference from the ground truth to obtain the training residual. We then perform DCT, discrete cosine transform, of the residual to find its dominant frequency omega 1. And add omega 1 to the Fourier feature, retrain the net, compute the residual, and find the next dominant frequency, omega 2. We compute omega 3 and repeat this until a given quality threshold is satisfied, or k reaches some predefined number. This is basically our adaptive frequency selection algorithm. For more details about the training procedure, loss function, and neural net architecture, please take a look at our short paper. Finally, I'll present our compression results. Here is a plot created by applying our method to 116 sequences randomly chosen from CMU mocap database. We fixed the number k of frequencies to see the relationship between compression ratio and reconstruction error. For k equals 6, a good number of sequences are compressed very well with a small reconstruction error. However, there are also sequences that have relatively high reconstruction error. For k equals 10, which means a larger network size, the compression performance becomes modest, but the reconstruction errors are generally very well. However, there is a motion that have high error even with k equals 10. We find that such a motion is often a corrected capture, as seen in the trajectory visualization of the character's feet shown at the right. Next, our method is compared to two baseline approaches, one based on SVD or singular value decomposition, and a variant of our method using naive choice of frequencies. SVD is basically a low-rank approximation of the animation matrix Y, and the naive choice means that the frequencies are consecutive integers, 1, 2, 3, and so on. We plot compression results of two example motions with various compression ratio. We can see that our adaptive Fourier feature net, shown in gray, consistently achieves the best compression reconstruction trade-off. This suggests that our neural implicit representation works well as compression algorithm, and the adaptive frequency choice actually improves the performance. This is the visual comparison of original and compressed motions. The red is the original motion, and blue is the 8 times compressed motion using our method. We can see that the difference appears to be very small. This is the same motion seen from another camera angle. Now let me summarize the presentation. We present a motion compression algorithm based on a recent neural implicit representation. We adaptively choose a few important Fourier feature frequencies during training using novel iterative training algorithm. We tested our algorithm with CMU mocap database and show that it can compress motions with small reconstruction error and performs better than baseline methods, such as the one using a naive frequency choice. Because in this study we compared our methods only with basic baseline methods, our future work includes a more rigorous comparison to other existing compression approaches. Also, learning how to compress common motion styles from a large motion dataset will be an interesting future direction. We release our implementation and the code is available at this GitHub link. This is the end of this presentation. Thank you very much for listening.